chapter is about the characteristics of sound. So I have already prepared the notes, short notes, because it's just a theory, mainly a theory part. We don't have anything quantitative here, it's just qualitative. These things we have already learned in O level also. But anyways, let's quickly go through this. There are three main characteristics: pitch, loudness, and then quality of sound. Sometimes for quality they use another term called timbre, but I don't think you are supposed to know that, but it's okay. These we don't use that term for quality, but what I have written in pink color, you can use those as the characteristics: pitch, loudness, and quality. So when you change these three factors of the sound, sounds, the way the nature of the sound we hear will be different. The first one is called the pitch. Pitch actually depends on the frequency. Okay, if you want me to give a slight idea about the pitch, imagine there is an instrument with strings like guitar or violin. When you have a thicker string and when you pluck that string, it will create a sound like dung. So that's a rough sound. But when you have a very thin string and when you pluck it, like in violin, it will give you ting ting ting, a sound like that, which is a sharper sound. So if the sound is sharper, that means the pitch is higher. If the sound is rough, that means the pitch is lower. Pitch is lower. And if you take birds, birds have a very sometimes they have this very sharp, annoying sound. So that is high pitch. But when you say a lion or a tiger, they have a very rough sound. That is, they have a low pitch. Those sounds have a low pitch. So mainly the frequency depends on the pitch depends on frequency, and when the frequency of the sound is high, the pitch of the sound will be greater. So if you want to physically observe it, you can use how sharp the sound is to compare. Okay, if the sharpness of the sound is high, that means it has a higher frequency as well as a higher pitch. Then I have chosen two graphical representations to compare pitch. Now these are two sound waves. Now you might have a question about sound waves. Now I have drawn transverse waves, but sound is a longitudinal wave. In longitudinal waves, it's difficult to plot the variation of amplitude and everything, because longitudinal waves, the particles oscillate like this. So for our convenience, we plot the sound wave as transverse waves for us to get an understanding. We are plotting just the amplitude. This amplitude we are plotting in this way. Okay, so don't get confused. Sound wave is not a transverse wave. This is just to understand the different frequencies. And so you can see here at a given time. Now if you take this as your time limit, I am taking this as my time limit. There you can see there are 1, 2, 3, 4 oscillations, complete oscillations. But in this you have only 2 complete oscillations. So let's say this is 1 second time interval, this time interval is 1 second. So this frequency is 4 Hz, this frequency is 2 Hz. Number of oscillations at a given time. Here we have higher, here we have lesser. So here we will have high frequency, this sound will have high frequency. So this sound will have higher pitch and this sound will be sharp. And this sound, but remember, now I have drawn both having same amplitude. So when you want to compare a property, you have to make sure that other properties are kept constant. All right, this is how it is. So they have same frequency, they have different frequencies, so their frequencies will be differing. And then how do you produce sounds of different frequencies? That depends on how fast the sound is produced. Okay, if a sound is produced faster, it has a higher frequency, but if the sound is produced slower, it has low frequency, something like that. Okay, I gave you real life examples also as to how you can compare pitch, and I hope you understood this. Okay, and women normally have higher pitch in their sound. Men normally have lower pitch because men have rougher voice. I hope you understood that. Right. Next is loudness. When I say loudness, it's all about volume. Okay, you all know about volume. In your radio, in your phone, in your TV, you can increase the volume, decrease the volume. When you increase the volume, high loudness. When you decrease the volume, lower loudness. Okay, so loudness has something to do with energy. That's what I have written at the bottom. Right, if your sound has higher energy, that means the sound will have higher loudness. Okay, if you want to shout, imagine you shout on a particular day for a longer period of time. It can be the sports meet, or if you are a teacher, you have to shout at your kids. Then at the end of the day, your energy will be drained out. You'll be very tired, because if you want to produce louder sounds, you have to put a lot of energy. But if you are speaking at a lower tone, You know, you are speaking to your friends, you can keep doing that. Not your friends, maybe you're just conversing with someone at a very light tone. That means you can converse for a longer period of time, because your energy doesn't drain out so soon, because for lower loudness you have to apply lower energy. So loudness is a factor which actually depends on amplitude, because we have learned that amplitude depends on energy. What's the relationship between amplitude and energy? We have learned under simple harmonic motion that energy is actually proportional to the square of amplitude. So when you increase the amplitude, energy will increase, so the loudness will increase. Okay, so loudness means it's actually the volume of sound. We all know what volume is. And then I am comparing two sounds. They have the same frequency. You can see here the time interval. If you take the time interval like this, 1, 2, 3 oscillations, 1, 2, 3 oscillations. So they have relatively lower frequencies, but you can see they have different amplitudes, lower amplitude, higher amplitude. So this is a sound which has higher amplitude, so it will have higher loudness. This is a sound which has lower amplitude, but it has so it will have lower loudness. Okay, so loudness is something which depends on energy. That's a key factor there. And then after pitch, loudness. Now pitch is how sharp the sound is, loudness is how strong, how loud the sound is, and then you go to quality. So there can be two sounds, they have same pitch or same frequency, same loudness or same amplitude, but still they might sound different to our ear. That is where quality comes. Okay, quality is something which depends on the instrument, or which depends on the sound source, or else if you put it in other words, it will depend on the nature of overtones created by that particular sound wave. Right, we already know. Now in O level you might have not heard this term overtone, but now since we have learned standing waves, we learned that in musical instruments, all the musical instruments produce standing waves. That is how they produce the sounds. So when standing waves are formed, there are overtones. Fundamental, first overtone, second overtone, goes on like that. So when you can change the nature of the overtones produced by the sound source, you can change the quality of sound source. Okay, so different instruments produce different quality of sound. There can be a guitar and a violin, both might be having the same frequency, same loudness, but still they will sound different to our ear. That is because of the nature of overtones they produce. Okay, so if you are supposed to represent loudness in a diagram, well, you can do it like this. I will draw a diagram now. Imagine a tuning fork. A tuning fork is a very simple sound source. It will create like a whistling sound, a very normal sound like this. Just a very normal sound, it can create normal sound like this. So at the meantime, if you have another instrument, like a musical instrument, it will have a complex nature of sound. So it might be like this, might go like this. You can see they both have the same frequency, correct, and same amplitude as well. But look at the nature of the wave. The nature of the waves are different because the sound source we used are different, or the types of overtones created during the sound formation are different. So these are the main three characteristics of sound. And one more thing about quality, there are some sounds which are really irritating. For example, when you are in the middle of a traffic jam, you will be hearing noises from all over the place, or you go to a market, very crowded street, it will be very irritating because you get sound from all over the place. So that sound has poor quality. But you listen to a very soothing sound, then that sound will have higher quality. I hope you got the difference. So pitch, loudness, quality. Pitch, how do you identify that? Based on the sharpness. If the sound is very sharp, that sound has higher pitch. If the sound is rough, that has lower pitch. Loudness, it's volume. When the volume is low, it has lower loudness. When the volume is high, it has high loudness. And quality, just explain how to distinguish between poor and good quality of sound. And that's all when it comes to characteristic of sound. The next part under sound is this, the audible range, and then infrasound and ultrasound. So when you say audible range, this is the your sound, the sound. If you want to hear a particular sound, if you want to sense a particular sound with a normal ear, then the frequency of that sound should be within this range, 20 hertz to 20,000 hertz. Okay, that is the range where the sound should be within that range. Okay, so you can hear 40 hertz, you can hear 10,000 hertz, but if the sound is low, if the frequency of the sound is lower than 20, you won't be able to hear it. If the sound is greater than 20,000, you won't be able to hear it. But different people have different ranges. Now small kids can hear sounds which are higher than 20,000, right? And older people, their range is much lesser. So for young, small kids, babies, the range is bigger, but for older people the range is lesser, something like that. Okay, that's how for different people the range might be different, but in general for a healthy human ear, this is what we normally, for a normal person, average person, this is the range we study, 20 hertz to 20,000 hertz. Sometimes they will give that this 20,000 hertz as 20 kilohertz also. Don't get confused, it's the same thing, 20 kilohertz. Fine. Right, now if there is a sound which is less than 20 hertz, in general we call it infrasound. Okay, the term infra means less, the term ultra means more. Okay, so if the sound has a frequency greater than 20,000, we call that sound ultrasound. That is how the terms infrared and ultraviolet come. Alright, infrared is below red, ultraviolet is above violet when it comes to frequency. I hope you can understand that. So if you want to describe infra sounds, they have low frequency. Since they have low frequency, they should have high wavelength. This is how the infra sounds are going to look like, with high wavelength. And ultrasounds have very high frequency, so they have very low wavelength. So they will be like this. I should have drawn it even closer. You get the idea, right? They have very low wavelength. Okay. So since the infrasounds have high wavelength, they have the ability of traveling for longer distances, kilometers. Okay, thousands. They have the ability of traveling for a range of thousands of kilometers. Okay, but ultrasound, when you take ultrasound, they have high frequency, they have very low wavelength, so they have the ability of traveling without bending straight lines. So they will not be disturbed by small objects, because they have very small wavelength, so they tend to move straight. When the wavelength increases, only they bend. They tend to bend. Okay, that won't happen. Now in real life, when it comes to infrasound, we are not able to produce infrasounds, but these animals such as elephants and whales, larger animals, they have the ability of producing infrasounds. Now when you consider elephants, they can detect another herd of elephants which are hundreds of kilometers away, just by sending infrasound from them. I mean, they can detect, they can hear infrasounds. Animals can detect infrasounds. Okay, so what are the uses of infrasounds? We can produce infrasounds, but we can't sense them with our ear, but we can detect them with advanced machineries, right? So the uses of infrasound are, you can detect all these natural disasters in advance. Now I have just listed some: volcanic eruptions, tornadoes, nuclear explosions, and avalanches. Avalanches are the kind of we have landslide in our countries. In countries which are closer to the North Pole or South Pole, they have these large glaciers. So when in glaciers we don't have landslides, we have avalanches. The snow, it slides, a large amount of snow, when it slides, it's avalanche. Very disastrous. It can be very disastrous. So we can detect avalanches which are happening at longer distances using the infrasounds produced by them. Okay, certain nuclear explosions were detected 10,000s of kilometers away from certain detecting centers. Okay, so nuclear explosions, all those things can be detected from a very large distance. And the other thing, sometimes this happens when you watch, especially when you watch horror movies in theaters. Okay, horror movies are already scary, but without you knowing, an extra fear and distress is caused by the infrasounds which are produced at theaters. Okay, it's not only because you are watching the movies, it's also because you are sensing the infrasound, not you are hearing them, but because of the infrasound that you will sense distress, fear in excess. Okay, for that purpose also infrasounds are used to create that real feeling, as if you are really in that movie. It will create that feeling when they use infrasounds. So these are the uses of infrasounds. You are supposed to know this, and you have to have a slight idea about infrasounds. Infrasounds are the sounds which have a frequency less than 20 hertz. And when it comes to ultrasounds, they are the sounds which have a frequency greater than 20 hertz or 20,000 hertz or 20 kilohertz rather, and they are actually produced by animals such as mammals such as bats and dolphins. So we already know that bats travel at night. So when a bat travels at night, it can't see anything. So what it does is it will send an ultrasound, and it will go and it will bounce back from the obstacle. So there is a time taken for the sound to return to the bat. So depending on that time, the bat's brain will automatically calculate the distance between the bat and the obstacle, so that the bat will not directly fly towards the obstacle. It will avoid the obstacle and fly. Okay, that is how bats, even dolphins, use the ultrasounds to avoid obstacles on their way. Okay, and as humans, we use ultrasound in sonar technology. Sonar stands for sound navigating and ranging. So this you might have learned in small classes also. Now imagine there is a sea, the sea, and then there is a ship. Now ship wants to detect what is underneath. So let's say there is a reminiscence or something like that underneath. Okay, or else the seabed. So what we do is we send ultrasound, and then the ultrasound will reflect and go back to the ship. Okay, so this is the distance we are supposed to find out. So you send the ultrasound when let's say time is equal to 0 when you send the ultrasound, and when you detect the ultrasound back, the time is equal to t. Okay, so the total distance traveled by the ultrasound is going to be d plus d. It travels 2d distance, that's the total distance. So you say 2d equal to, you know, the speed of the ultrasound v into the time taken for the ultrasound to return t. So using this equation, so d is going to be equal to v into t over 2. V is the speed of ultrasound, t is the time taken for the ultrasound to be detected again in the ship, and when you divide by 2, you will get the distance to that particular, what do you call that, obstacle. Same way submarines use this sonar technique to identify the obstacles in front, just like bats, submarines also use. See, you send a wave, it bounces and comes back to the submarine. Time taken is t, distance travel is d plus d, 2d, same thing. So these are some uses in marine applications. Marine stands for the all your activities with regard to sea. And then in medical purposes, we use ultrasound to detect to form ultrasound scanning, to form images, ultrasound images. What are those images? For example, we scan to see how the baby is doing, the condition of a baby. So what happens there is, imagine this is the baby. Okay, so you send ultrasound, and the ultrasound will bounce back from the boundaries. Now around the baby, that's a different medium, baby is a different medium. So when ultrasound travels from one medium to another medium, there is a change in density between the media, right? So the ultrasound will detect where the density changes. So they say at different points, when ultrasound bounces back, so it will detect all these points one by one, and you will see the image of the baby. Okay, you will not see an image like you see from a camera, but you see a rough image of baby. Not only that, we can detect blood clots inside veins, and inside veins you can you can detect blood clots. You can detect the speed of blood flow, all those things using the sonar technology, right? Or else the ultrasound technology. Now I have written here, in ships to detect depth, direction and speed of obstacles. Not only depth, you can detect speed. If you want to detect speed, I hope you can remember, you have to use what, Doppler's effect. Using Doppler's effect, you can find the speed. Not only that, you can remove cataract in the eye and kidney stones using ultrasounds. Now how does that happen? Now we know cataract in the eye in the sense, you have the eye like this, you have the eye, and cataract means a small layer formed in front of your eye lens. That is what cataract is, right? I hope you can remember, that is what cataract is. So we need to remove this. What we do is we send these ultrasound waves. So ultrasound waves have a very high frequency, so you will be vibrating very fast. So as they vibrate, they will strike this cataract, and slowly the cataract will break and get destroyed, the cataract. Okay, same way in kidneys we have sometimes we have these kidney stones created inside kidneys. So those kidney stones must be removed, but you can't directly remove the kidney stones. Imagine these are the kidney stones created inside kidneys. So again, what you do is you send these ultrasound waves. They are at very high frequency. So what happens is these ultrasound waves will strike or collide with the stones, and the stones will be broken into small, very thin, fine particles. Okay, so then those fine particles can be removed with the urine, and then the kidney is safe. So that's how ultrasound is used to remove cataract and kidney stones. And also in industrial, when it comes to industrial usage of ultrasound, so these two are medical usage. I said another one, you can identify blood clots also inside veins. These are marine applications, medical applications. This is going to be industrial application, that is to detect cracks inside metals. Okay, sometimes you have a metal, for example, think of this as a metal. Okay, we don't know what is inside this. So what we do is you send ultrasound, and then if there are cracks inside the ultrasound will bounce back if there is a crack. Okay, so you can identify whether there is a crack, and you can identify where the crack is to using ultrasound inside the metals. So this is a rough explanation about infrasound and the audible range and the ultrasound. Yeah, you have to know a rough introduction about both the sounds and also the uses, because probably they will ask in MCQs, and these small calculations you should be able to do. I think these things were there in O level. I have explained this here also. These sounds, they travel at constant speed, so you can use this equation and get the answers.